G'day, it's James again. So what's the mathematics behind these personal polynomials? How do you write out a formula that spells your name? Well, the best way to explain it is just to do it. In fact, I'll do two examples with you. Let's spell go and let's spell math for go math. All right, so I'll do the simpler one first. Let's do go, just two letters. G, the 7th letter of the alphabet, O, the 15th. So I want some formula that gives me 7 when I put in x equals 1 and gives me 15 when I put in x equals 2. So how can I create such a formula? Well, I'll do two pieces, one for the 7, one for the 15. So let me start by just writing down a 7 and a 15 piece. All right, let's think through what needs to happen here. When x equals 1, I want the 7 piece to survive, but I want the 15 piece to go away. So when x is 1, I want this part to disappear. How can I make a piece of a formula disappear for x equals 1? Well, one way to do it is to put in a factor of x minus 1. When x is 1, I get 15 times 1 minus 1, 15 times 0. Indeed, that piece will go away. It's going to be 0, and there's the 7 unaffected. All right, grand. I also want the same thing to happen for the 15 piece when x equals 2. That is, I want x equals 2 to have a piece 15 survive, and this piece 7 to disappear for x equals 2. So how to make this part disappear for x equals 2? Let's put in a factor of x minus 2. So there's my two pieces of a polynomial that looks like they're doing the right thing. In fact, let's double check. Let's put in x equals 2. Do I indeed get 15? 7 times 2 minus 2 is 0. 7 times 0 is 0. Plus 15 times 2 minus 1. 15 times 1, 0. Plus 15 is 15. Beautiful. And when x equals 1, I should get 7. I get 15 times 0, 1 minus 1. Yep, that piece disappears. 7 times, 1 minus 2, negative 1. 7 times negative 1. I'm getting negative 7, not 7. Bother. Okay, let's not give up hope. What can we do? How can we fix this problem up? Well, the problem is we've got 7 times negative 1 here. What if I made this a fraction with a negative 1 on the bottom? Can you see what's going to happen then? I'll get 7 times negative 1 over negative 1. A fraction over the same thing is just 1. 7 times 1 is 7 plus 0. When x equals 1, this formula now gives me 7. Beautiful. There it is. There's a formula that spells go. Now, it looks pretty messy right now, but I can make it a little bit simpler. For example, this is really what? 7x minus 14 over negative 1 plus 15x minus 15. Or that negative on the bottom, because it really makes this 14 minus 7x plus 15x minus 15. So what does that give me? That gives me 15x's, so we said there's 8 x's, 14 minus 15 minus 1. There is the formula that spells go, 8x minus 1. Grand. All right, so what I want to do now is give you the polynomial that spells math. It's going to use exactly the same idea. I'm going to have 4 pieces, one for 13, one for 1, one for 20, one for 8. I'm going to arrange those pieces so they disappear at all the right spots and only survive at the correct spots I want. But then I might have to do some adjustments to balance out whatever happens to the numerator. I better counterbalance it with something going on in the denominator for me. So it's going to take me a little while. What I'm going to write down is going to be a visual nightmare, but I bet we can see our way through the visual clutter and understand what's going on. So I'm going to speed up the video as I go on. So you have to watch me first clean the board, and then you have to watch me write the whole thing, and I'll be right back and we'll check that formula I wrote down is really doing what we want it to do. I want it to spell math. All right, here goes. Sped up video. Beautiful. Now I'm back. Here is my formula for the word math, and I'm going to show you that it works beautifully. In fact, I did exactly the same strategy before. It looks like a visual nightmare, but actually conceptually it's just as straightforward. Here goes. Let's check. I claim when you put in x equals 1, you will get the number 13 out of this weird formula. In fact, I've got 4 chunks. You can see them. One for 13, one for 1, one for 20, one for 8. I've designed the latter 3 chunks to disappear for x equals 1. There's a factor of x minus 1. Disappears. Factor of x minus 1. Disappears. Factor of x minus 1. Disappears. So when x is 1, all that's 0, all this is 0, and all this is 0, only this piece could possibly survive. And when x actually is 1, I've got 1 minus 2, 1 minus 3, 1 minus 4 on the numerator. But look, 1 minus 2 is negative 1. 1 minus 3 is negative 2. 1 minus 4 is negative 3. So I've designed the denominator to exactly match the numerator at x equals 1. So when x is 1, all this is just something divided by the same something is 1. 13 times 1 plus 0 plus 0 plus 0 does indeed give me 13. In fact, you can check that I'll do another one. I'll do x equals 3 just to make sure we've got it right. I've designed it so that 3 factors disappear when x is 3, but only this factor survives when x equals 3. In fact, guess this first term does disappear for x equals 3. The second term does disappear for x equals 3. And so does this one. It also disappears for x equals 3. So 0, 0, and 0. This piece survives. And when x is 3, I've designed the denominator to match the numerator. 3 take away 1, 3 take away 2, 3 take away 3. So when x is 3, this is 20 times 1, outputs 20. Go math, look at that. Now this is a polynomial, it's pretty ghastly right now, but I could simplify. For example, 1 times negative 1 times negative 2 is indeed just a 2. I can make that look simpler. 3 times 2 times 1 is 6. So I can go that way, then I can start expanding all these terms and get a single polynomial in terms of powers of x, which is going to have some pretty ghastly fractions to it, by the way, but there it is. We can now see what's going on. It's just a matter of algebra there, pretty tedious algebra to make it look like a polynomial, but bingo, that's the idea behind this. That's all I was doing all along through these personal polynomials, and you know what, it's just fantastic stuff. So, indeed, go math!